Okay, question 8. So we've got a wave diagram drawn for us, and it says use figure 12 to calculate the wavelength of the wave. And what's made this tricky is normally we'd go, so if I just sketch a wave, we go from peak to peak, or if I carried that down, trough to trough. But in this example, we can't see where the next peak is, okay? And we can't see where the trough is over there. So what we do know, though, is we have half a wave on the screen. So if I go from that point to that point, that is half of the wave. The other half is going to be over there. So at least I can work out half of the wave, and that's going to be where it crosses here, which is at 14. So I need 2 lots of 14. That will give me the full wavelength. So half the wavelength is 14. The full wavelength, 14 times 2, is 28 centimetres. Next one, a student sitting on the shore of a lake and they're watching ripples. So these ripples are moving towards the child, and that boat is going to bob up and down as the energy from the wave passes by. The student has a stopwatch. Brilliant. Describe how they could determine the frequency. So now frequency equals the number of waves divided by the time. So what they're going to do, pick a point. So pick your boat there. So I'm going to pick my boat as the point. I'm going to start my stop clock for, say, 60 seconds, and then going to time how many times this bobs up and down. So I can do its bobs over time if I wanted to. But the basic idea, pick a distance, count the number of waves that pass that point over a certain time, and I'm going to pick 60 seconds a minute. So frequency is the number of waves each second. Pick a point on the surface. I'm going to pick the boat. Time for 60 seconds using the stop clock or stopwatch. Count the number of waves that pass that point in 60 seconds. Frequency equals the number of waves divided by 60 seconds. Done. Next one, we've got our foxes stab wolves. So if I do that here, so foxes stab wolves, or as it's written in here, frequency equals the velocity divided by the wavelength, lambda. They are the same equation. And it says calculate the wavelength. So we want to find out W. So we know W equals S over F, which equals velocity over lambda. And then we're away. So the speed's there, the frequency's here, with no unit changes there. So if I just rub that out, and then I can put in the model answer. So W equals S over F. The 1.5 is the speed, divided by the frequency 0.7 equals 2.1 meters. On to the next one. Water waves are transverse waves. Describe the difference between transverse and longitudinal. So I've tried to teach it V, P, D, O, E, T. And what we've got is energy moving in each. And then we're going to have an oscillation or a vibration. And that can either vibrate that way or vibrate that way. This way it's perpendicular. That is a transverse wave. And if it's parallel, it's a longitudinal wave. So this is light and water, transverse, light and water, and a longitudinal wave, sound and primary seismic waves. So now we've just got to put the VP, DOET together and explain it for transverse and explain it for longitudinal. So in a transverse wave, the vibration, oscillation, is perpendicular to the direction of energy transfer. In longitudinal, it's parallel to the direction of energy transfer. And then the last one is, it tells us sound waves travel at 330 meters per second. So we've got a speed there or velocity. The student hears the sound, that's T. Calculate the distance, that'd be D, or if it was a displacement X. And we can see we're after X. So we just need to take the speed, 330, multiplied by 4. And that's it, done. A lot easier than the previous question.